Hello everyone. Today we will talk about the inference on the difference in means of two normal distributions with variance is known. The inference for the difference in means of two normal distributions with known variances is commonly used to compare two population means in fields like manufacturing, pharmaceuticals, education, and finance. It tests whether the means of the two groups differ significantly, often applied in quality control, treatment comparisons, and performance evaluations. We must always assume that populations are normally distributed and the variants are known. Null hypothesis. A null hypothesis is a type of statistical hypothesis that proposes that no statistical significance exists in a set of given observations. The formula for a null hypothesis is H sub 0 is equal to micron sub 1 minus micron sub 2 is equal to delta 0, while the default of delta 0 is equal to 0. The alternative hypothesis is a statement used in statistical inference experiments. It is contradictory to the null hypothesis. The alternative hypothesis has two formulas, one for two-tailed and one for one-tailed. For two-tailed, for two-tailed, for two-tailed, it is micron 1 minus micron 2 is not equal to delta 0, while on one-tailed, it is either micron 1 minus micron 2 is greater than delta 0 or micron 1 minus micron 2 is less than delta 0. The formula for the statistic is as follows: x sub 1 minus x sub 2 minus micron 1 minus micron 2 all over the square root of O sub 1 over n sub 1, O sub 1 squared over n sub 1 plus O sub 2 squared over n sub 2. The x sub 1 and the micron 1 and micron 2 is a true means of two populations being compared, while the O sub 1 and O sub 2 is the true variances of the two populations. These are assumed to be known. The x sub 1 and x sub 2 is a sample means of the two populations based on collected data, and the n sub 1 and the n sub 2 are the sample sizes of the two populations. The decision rule. It determine to determine the significance level. The significance level is commonly chosen as alpha is equal to 0.05 and the critical values. The critical values for a two-tailed bell curve is reject the null hypothesis if z is greater than z sub alpha over 2, or on a one-tailed bell curve, reject the null hypothesis if z is greater than z sub alpha for the upper, or z is greater than negative z sub alpha for lower. P-value approach. The p-value represents the probability of obtaining a test statistic as extreme or more extreme than the observed value, assuming the null hypothesis is true. Decision rule. Reject the null hypothesis if p-value is less than or equal to alpha, usually 0.05, indicating strong evidence against the null hypothesis. Fail to reject null hypothesis if the p-value is greater than alpha, suggesting insufficient evidence to disprove null hypothesis. As for example, suppose that our x sub 1 is 25 and our x sub 2 is 20 and the variance sub 1 is 16 and variance sub 2 is 25, while our n sub 1 is 50 and n sub 2 is 60, while our delta 0 is equal to 0. SE stands for statistical error, and the formula for that is this: square root of O sub 1 over n sub 1 plus O sub 2 over n sub 2, which we input the given value of 16 and 25, and our n sub 1 and n sub 2 is 50 over 60, which will give us the square root of 0.32 plus 0.4167, which is equal to 0.8154. Now our z is equal to x sub 1 minus x sub 2 minus delta 0 all over the SE, or the statistical error, which is 25 minus 20 all over 0.8154, or 5 over 0.8154, which is equal to 6.13. For alpha is 0.05, z sub alpha over 2 is equal to 1.96. Since 6.13 is greater than 1.96, reject the null hypothesis. The p-value is effectively 0, much smaller than 0.05, so reject the null hypothesis. I hope you've learned something today, and that's all, and thank you for watching.
So, inference on difference in means of two normal distribution, variance, and norms. So, what is inference? So, it refers to the statistical process of testing whether there is a significant difference between the means of two population or groups where both populations are assumed to follow normal distribution, but the variances are unknown. Next is the problem setup. First is the two independent samples. So you have two groups or populations, each with an unknown mean and variance. Second is assumption of normality. So the populations from which the samples are drawn are assumed to follow normal distribution. And the last one is unknown variances. So this is both populations have unknown variances, and these variances may not be equal. So here are the key concepts. First is the hypothesis testing. So you're testing the hypothesis that the two population means are equal versus the alternative that they are different. And second is the two sample t-test. Since the population variances are unknown and the sample sizes might be small, the two sample t-test is appropriate. And the last one is the unequal variances. If the population variances are unequal, you use Welch t-test, which is a variation of two sample t-tests that adjust for unequal variance. So, hypothesis. The null hypothesis, the means of two populations are equal. And the alternative hypothesis, the means of the two populations are different. Just like this, as what we can see in the picture. The degrees of freedom of the Welch t-test are calculated using the Welch-Slattern weight equation. So this is the formula, accounts for the fact that the variances are not assumed to be equal. Steps to perform the test. First is collect data. Obtain the two independent samples. For each sample, calculated the sample mean and sample variance. Second is state the hypothesis. Whether it's null hypothesis or the means of the two populations are equal, or the alternative hypothesis, the means of the two populations are not equal, or one is greater or less than the other, depending on the test. And the third one is to calculate the test statistic, or to compute the sample means of the x sub 1 and x sub 2 sample variance, or the s squared sub 1 and the s squared sub 2, and sample sizes, or the n sub 1 and n sub 2, and compute the t-statistic using the formula above. Number 4, determine the degrees of freedom. Use the Welch-Slater-Weight equation to calculate the effective degrees of freedom. Number 5, find the p-value. How are we going to find the p-value rather? So once you have the t-statistic and the degrees of freedom, use the t-distribution to find the p-value, which is the probability of observing a t-statistic as extreme as one calculated under the null hypothesis. And the last one, the number 6, make a decision. So if the p-value is less than the chosen significance level, reject the null hypothesis and conclude that the means are significantly different. So if the p-value is greater than the significance level, fail to reject the null hypothesis, indicating that there is not enough evidence to suggest a significant difference between the means.
So hello everyone, my name is Kines Lacson, and this is the continuation of Lauresta's report. So let's start with example. So sample 1. Sample 1 has 3.8, 4.0, 3.6, 4.1, and 4.3, with a mean of 2.94, a variance of 0.053, and a sample size of 5. In sample 2 is 3.8, 4.0, 3.6, 4.1, and 4.3. And its mean is 4.04, variance of 0.027, and a sample size of 5. So the difference between sample 1 and sample 2 is its mean and variance. So we have 4 steps to follow. In the first step would be calculate the t-statistic. So t is equals to 2.94 minus 4.04 over the square root of 0.053 over 5 plus 0.027 over 5. So that would equal to as negative 1.10 over the square root of 0.0106 plus 0.0054, and that would equal to as negative 1.10 over the square root of 0.016. So further simplification, that would equal to as negative 1.10 over 0.126. So dividing negative 1.10 over 0.126 would equal to as negative 8.73. So in the second step would be calculate the degrees of freedom using the Welch-Satterthwaite formula. So df is equal to as 0.053 over 5 plus 0.027 over 5 raised to 2 over 0.053 over 5 raised to 2 over 4 plus 0.027 over 5 raised to 2 over 4, and that would equal to 7.8, rounded to the 8 degrees of freedom. In the third step, find the p-value. Using a t-distribution table or a statistical software, find the p-value corresponding to the calculated t-statistic and degrees of freedom. In this case, the t-statistic of negative 8.73 with 8 degrees of freedom gives a very small p-value, indicating a statistical significant difference between the means. And the last step would be conclusion. Since the p-value is less than 0.05, we reject the null hypothesis and conclude that there is a significant difference between the means of the two populations. Assumptions. There are three things to assume, and the first one would be normality. The second would be independence, and the last would be unequal variances. So normality. The population should follow the normal distribution. This assumption is crucial, especially for small sample sizes. If the sample sizes are large, typically n is greater than 30, the central limit theorem ensures that the sampling distribution of the mean is approximately normal, even if the original data is not. Independence. The samples must be independent of each other. And lastly, unequal variances. The Welch t-test is specifically designed for cases where the variances are unequal. So in summary, inference on the difference in means of two normal distributions with unknown variances typically involves using Welch t-test to assess whether the means of two independent samples are significantly different. This test is robust to unequal variances and is widely used in practical statistics. The test statistic follows a t-distribution with degrees of freedom estimated via the Welch-Satterthwaite formula. The p-value helps determine whether to reject the null hypothesis, providing evidence of difference in population means. So that's all. Thank you.
Inference of the variance of two normal distributions. And this topic will be reported by Mangolamas and Leonidas.
Introduction to Problem and Basic Concepts. Introduction to Statistical Inference. Statistical inference refers to the process of using data from a sample to draw conclusions about a population. One of the key concepts, or one of the key aspects of statistical inference involves imitating the parameter of a distribution. Problem statement. We are concerned with comparing two normal distributions with unknown variances. In practice, many real-world problems require us to determine whether the variances of two groups are equal or different, which is important for the hypothesis testing and decision-making in fields like medicine, economics, and engineering. Importance of variances. Variances represents the spread of dispersion of dataset. When comparing two normal distributions, the variances inform us about consistency or the variability within each group. Thus, understanding the variances help us in determining reliability of the data. Definition of normal distribution. The normal distribution is continuous probability distribution characterized by its bell-shaped curve. It is defined by two parameters, the mean and the variance. The formula for the probability density function is given by. Here is the formula. Then next is K properties of normal distribution. Normal distribution
are symmetric around the mean, and about 68% of data lies within one standard deviation of mean is 95% with two standard deviation of 99.7 within the three standard deviation. Here is the chart of standard normal distribution. Next is the problem of inference of variances. In many cases, comparing to normal distribution, we interested is testing hypotheses about the variances. For example, we might want to know if variances are equal across the populations, or we might want to estimate the variances of each distribution based on sample data. Interference about variances often involves the use of sample data. The goal is to make conclusions about the population variances. This typically involves hypothesis testing or confidence intervals for variances. This is the another chart.
Methods for inference and hypothesis testing. Hypothesis testing for variance comparison. The F-test for equal variances. One common method for testing if two populations have equal variances is the F-test. This test compares the ratio of two sample variances and the statistic calculated as F is equals to S sub 1 squared over S sub 2 squared, where S sub 1 squared and S sub 2 squared are the sample variances from each population. Assumptions for the F-test. The F-test assumes that both populations are normally distributed. Additionally, the two samples should be independent of each other, and the data should be continuous. In the decision rule, we compare the calculated F statistic to a critical value from the F distribution table, based on the significance level and degrees of freedom. If the F statistic exceeds the critical value, and the null hypothesis that the variances are equal, confidence interval for the variance of a single normal distribution. Chi-square distribution for variance. When estimating the variance of a single normal distribution, we often use the chi-square distribution. The formula for constructing a confidence interval for the population variance is sigma squared is based on the sample variance S squared and the chi-square distribution. Confidence interval formula. For a given confidence level, the confidence interval for the population variance is calculated as n minus 1 times S squared divided by the chi-square of alpha over 2 to n minus 1 times S squared divided by the chi-square of 1 minus alpha over 2, where n is the sample size, S squared is the sample variance, and chi squared alpha over 2 and chi squared of 1 minus alpha over 2 are the critical values from the chi square distribution for the chosen confidence level. Testing hypotheses about the variance of one population. We also use hypothesis tests to evaluate the variance of one normal distribution. For example, we may wish to test if the variance of a population is equal to a specified value of 0 sigma squared. The test statistic for this hypothesis test is x squared is equals to n minus 1 s squared over 0 sigma squared, where s squared is the sample variance and 0 sigma squared is the hypothesized variance and n is the sample size. So in the decision rule for chi-square test, we compare the calculated chi-square statistic to the critical values from the chi-square distribution table. If the statistic lies within the rejection region, we reject the null hypothesis. Practical considerations and assumptions. It's important to ensure that the assumptions behind this test are met. For example, in the case of the F-test, the populations should be normally distributed, and the samples should be independent. Additionally, if the sample sizes are small, the test may not be reliable, and we may need to use non-parametric methods or other techniques for variance estimation.
So, next is conclusions and final thoughts. In conclusion, we discuss how to perform inference on the variances of two normal distributions. We covered by hypothesis testing techniques such as the F-test for comparing variances and the use of chi-square distribution for estimating and testing variances. We also emphasize the importance of meeting assumptions behind these methods, such as normality and simple independence. Next is practical application. Understanding the variances is crucial in many real-world applications. For instances, in manufacturing, comparing the variances of production process can help determine if one process is more consistent than other. In the medical students, comparing the variances of treatments effects guide decisions about which treatment is more reliable. In summary, in interference of variances of two normal distribution plays an important role in statistical analysis, and mastering these techniques is essential for making informed decisions based on data.
Hello everyone, my name is Daniel Marcel Lumino, your next reporter in the last reporter for this group. The report is Interface the two population proportion. Interface the two population proportion is a statistical procedure that compares two population proportion to draw conclusions about the difference between them. It can be used to estimate difference to population proportion with confidence interval or attest a claim about difference with hypothesis test. Here are some things considered when the producting interference for two population proportion. Number 1 is samples. The sample should be a simple random samples that are independent. Remember it's independent. Number 2 is a sample size. The population should be at least 10 or 20 times the size of the sample to avoid oversampling. Number 3 is number of successes and failures. For each samples, the number of successes and failures should be at least 5. Null and alternative hypothesis. The null hypothesis is the two proportions are equal, and the alternative hypothesis is one of the following. Close open parenthesis H, close open parenthesis A, P1, P open parenthesis 2 less than 0, or close open parenthesis H, A, P close open parenthesis 1 minus P close parenthesis 2 and 0. This statistic account for both samples and p-value. Use the normal distribution for find the p-value for the test. In the confidence interval, a reasonable point estimate of the difference is slash close open parenthesis slash p close open parenthesis 1 slash p close open parenthesis 2. Interface of two population proportion typically refers to the statistical analysis used to compare the proportion of central characteristic of two different populations. Step to compare two population proportions defines the populations. Identify the two populations you want to compare. For example, you might want to compare the proportion of smokers in two different cities. Collect data. Gathering data from both populations. This usually involves take random samples for each population and recognize the number of success, the number of the smoker, and the total sample size. Let close and open parentheses in 1 be the sample size of the first populations. Let close open parentheses x1 be the number of the successes in the first population. Let close open parentheses n2 be a sample size of the second population. Let close open parentheses x2 be the numbers of success in the second populations. Calculates a sample proportion. The sample proportion for the first populations is this, and the sample proportion for the second populations is this. Formulate hypothesis. Null hypothesis is close open parenthesis h0 is equal to close open parenthesis p1 equal to p2. The proportion are equal. And next is alternative hypothesis. Close open parenthesis HA close open parenthesis P1 ni P2. The proportions are not equal. Calculate the t-statistic. The t-statistic from comparing two proportion can be calculated is the formula. And this is the formula. Is the pooled sample proportion, and this is the pooled sample proportion. Next is determine the significance level. Choose a significance level commonly close parenthesis slash alpha equal to 0.05 seconds. Next is find the critical value. Use a standard normal distribution able to find the critical z-value corresponding to your significant level. Make a decision. If the absolute value of the calculated z is greater than the critical z value, reject a null hypothesis. If not, fail to reject the null hypothesis. Interpret the results based on your decision. Interpret the result means is the context your population. For examples, suppose you want to compare the proportion of people who support a new policy in two different cities. City A, 60 out of 100 people support the policy. In the city B, 45 out of 80 people support the policy. Calculate the sample proportion. And this is how you calculate it. Calculate the pooled proportion and calculate the t-statistic. Next is compare the z-value to the critical value and make a decision. This process allows you to statistically infer whether there is a significant difference between the two population proportion. This process allows you to statistically infer whether there is a significant between the two population proportion. Thank you for listening, and that's all. Thank you.